today's lesson we're going to be talking about artificial radioactivity. We've discussed alpha and beta decay, and those occur naturally on Earth. But there's other ways we can create radioactive elements or even new elements through a process called transmutation, which is a form of artificial radioactivity. So here's just a summary of our two natural radioactive decays. So remember, alpha decay, we're emitting that alpha particle, so 4/2 with the alpha symbol, or sometimes we use the helium symbol as well. Beta emission, or beta decay, we're ejecting that electron, so the 0/-1. So those are the two natural forms of radioactive decay. Now we're going to talk about the artificial type. And so it all started, again, with Ernest Rutherford. His name has come up a lot. So in 1919, he took a container of nitrogen gas, and you can see a picture of that over here on the right, and he enclosed that gas in a glass tube, and then he bombarded it, so he shot alpha particles at that gas. When he was done with that, he then analyzed that gas, and what he found in the tube was not nitrogen anymore. It had actually been converted into oxygen. And so you can see here the picture of the reaction that took place. So we took our alpha particle, so our 4/2 He, we hit the nitrogen atom with it, and it actually kind of absorbed what we think of absorbing it, and then it shot out a proton. And so that nitrogen was converted or turned into a new element. And so we call this process of creating a new element or converting one element into another artificially, we call that transmutation. And so transmutations were kind of limited in Rutherford's time, but in 1930 we were able to produce high enough energy particles to actually bombard more elements to create new ones. And so in 1930, particle accelerators were developed, and so we could produce those high energy particles to shoot them at other elements. And we were able to create many, many other synthetic elements, some of which were radioactive. And so the first artificial radioactive isotope that was produced was in 1934 by Irene and Frederick Joliot-Curie. So Curie's daughter and son-in-law continued the work of her parents, Pierre and Marie, and were able to create the first artificial radioactive element. So they took aluminum, bombarded it with some alpha particles, and it produced phosphorus-30, which is radioactive, and it gave off a new element that we haven't talked about yet, is a neutron. And so this process of bombardment generally involves 4 particles, but sometimes it could be 3. And so we have the target nucleus, so the stable isotope that we're going to be shooting. So in the last example, they took aluminum, 27. Then they had a projected particle, think of it like the bullet. So in this case, the projected particle was the alpha particle, was being shot at the aluminum. Then we produce a new kind of atom or new element. So here our product nucleus was phosphorus-30. And then a lot of times you'll eject another particle out. And so the ejected particle is usually the lighter one. In this case it's the neutron. So that's a new particle we're going to be using. So the neutron symbol is 1/0n. So the 1 telling us it has a mass number of 1, so 1 neutron. And it has no atomic number because it's just a neutron, so 0. Let's try an example here. So nobelium, named after the Nobel Prize that's given out, can be produced by bombarding curium with a projected nuclei of a lighter element. That element can be identified by completing the following equation. So we're going to follow our same rule. We want the total sum on the top on the left to equal the total sum on the top on the right, and same thing in the bottom. We want the bottom numbers to sum to be the same number as the number on the right. So right now, if we're looking at our equation, on our left side we have 246. On our right side we have a couple numbers. So we have 254. And then if you notice, there's a big 4 out front. That means we're giving off 4 neutrons. And so our total number on top is going to be 4 times 1. So we have 4 as well. So right now we have 258 on our right side. And so we need to get 258 on the other side. So quick little math, we're going to take 258 and we're going to subtract 246, what we have on the left, and we're going to get 4 over here. So our top number of whatever our particle is going to be 4. So it's looking like it's going to be an alpha particle, but let's just double check. So on the left side we have 96, on the right side we have 102, and now we have 4 times 0, which is just 0, so we have 102 on this side. So to get from 96 to 102, we're going to do a little subtraction there. And I actually did this top one wrong, sorry. This should have been a 12. Double checking my work there. And we have 102 minus 96, and we get 6. So if we're going to look on our periodic table for element 6, and element 6 happens to be carbon. So for this bombardment reaction, this transmutation, we projected a carbon atom at curium, and we produced nobelium, and we ejected 4 neutrons. So let's label those. So our ejected particle, I'm going to label it this. Okay. Our particle we shot at. Okay. Our stable one. And then our new element that formed was nobelium. Okay, let's try another example. So here we want to complete the following equations by supplying the missing numbers or symbols, and then we want to name each particle that we produce and identify whether we have a target nucleus, a projected particle, a product nucleus, or an ejected particle. So let's try the first one. So our first question mark, we have to figure out what element is 56 over 27. So we look at 27 on our periodic table, and 27 is cobalt. So I'm going to write right below what it is. So it should be cobalt. Next we're going to look at the next particle. So we have 0 or question mark over question mark with an N. So N stands for our neutron, and so neutron is 0 over 1. Okay. And then we have to figure out what we make. So we have 60 over question mark with another question mark. So remember, we've got to get the bottom numbers to equal and the top numbers to equal. So let's figure out what the bottom number should be. So on this side we have 28 and a 1. So that means on this side we have to have 29. And then we look up on our periodic table, what is element 29? And element 29 is copper. Okay, let's try the next one. So we're going to look up on our periodic table, what is element number 42? So element 42 is molybdenum, MO. Okay, now we have our hydrogen. So hydrogen, we look up on the periodic table, has a 1 for its atomic number. And normally hydrogen has 1 proton, 1 neutron. So our total mass number would be 2 on the top. Okay, then we're going to look on our periodic table for number 43 to get the element symbol. And 43 is, I believe, technetium, TC. Okay, and then our last one, we're going to label the particle. So 0 over 1 is our neutron, so we'd write an N for that blank. And then our last problem, this is supposed to be a plus sign there. So we're going to look up, what can we fill in first? So we can fill in our top question mark here. So we know on this side we have 58 and 209. So if we add those together, we should get a sum for those two. So 58 plus 209 gives us 267. So that's what the top number has to equal on the other side. So we already have 1. So that means this number has to be 266, plus our 1 gives us the same number. We can fill in this particle over here. So 1 over 0, that would be our neutron symbol. Okay. Bismuth, we can look up on our periodic table. So bismuth, Bi, is number 83. So our question mark here would be filled in with an 83. And now our last one, we need to figure out the total on the bottom. So right now we have 109 on this side and only have 83 on that side. So to get to 109, we're going to take 109 minus 83. And that gives us 26 for this one. And then we look up on our periodic table, what is element 26? And that is iron, so Fe. So kind of work through the problems, filling in with what you can, making sure the top number is equal, the bottom numbers are equal on both sides of our reaction, just like we were before. So the last thing is a lot of times we use this process of bombardment or transmutation to make or develop or discover new elements. So in 1940, a group working out of Berkeley in California with Glenn Seaborg were able to synthesize and discover 10 new elements, 94 through 103, which is an amazing feat that they were able to do. And so we call these elements, a lot of these elements, trans-uranium elements because they were added, or they have atomic numbers greater than uranium. And so a lot of his work was this row down below here. And they actually pulled these 2 rows out of our periodic table just to condense it down. And you'll notice those at the bottom of the periodic table. And he actually has an element named after him, seaborgnium. And he was actually the first person to still be alive when the element was named after him. So this is a picture of him on that day where the element was officially named, seaborgnium.